Hey, welcome to the second order mechanical system lab. This includes a differential equation with damping, so you have that C x dot term. So going through the lab, we have this cantilever beam and dash pot apparatus with a mass and an accelerometer attached to it. The accelerometer then gets wired over here to the Elvis board. Make sure you follow the appropriate diagram on the lab handout, which shows you where to ground, where to put in the 5 volts, and which terminal to use for the acceleration output. So just going through the lab step by step, the first step is to take a ruler and a force gauge, and we don't have enough force gauges to go around, so bear with us and just pass them around and share them. So you'll line the ruler up so that the beam position is initially 0. You'll then take the force gauge, and using the force gauge, you'll pull on the beam until you get to the 5 Newton mark. You'll measure the displacement of the beam. So remember, F equals K delta X. So the displacement times the force divided by the displacement will give you the beam spring coefficient. Then following that, you attach the accelerometer as such using double-sided tape. Run the wires along the beam over to the Elvis board to avoid the wires interfering with the vibrations. And then the dash pot will start off at a minimum damping position. So it'll start off with minimal damping. As you continue through the lab, you'll tighten the screw using standard right-handed screw principle, so righty tighty, lefty loosey. And then after that, you have everything set up on the Elvis on LabVIEW, and you're ready to go. So you'll start off with the Elvis board, and in LabVIEW you'll press play. After you displace the beam roughly 1 inch, when you press run, you let the beam go and watch it oscillate. It'll reach steady state where it's not moving, and looking over to LabVIEW, we have this nice oscillating curve. So following that, you'll then take a screwdriver, you'll tighten the screw roughly 1/2 turn and do the same thing, continuing on until you get to an overdamped condition. So right now it's very overdamped, I can't even push it in, and it's barely oscillating at all. So once you're through with that, that's basically the entire lab. So congratulations and good luck. Now, to calibrate the accelerometer, just like you did with the thermistor where the relationship is linear between the resistance and the temperature, here we have a linear relationship between voltage output from the accelerometer and the acceleration in the accelerometer. So here on the accelerometer, you probably won't be able to see it in the video, but there's an x-axis, a y-axis, and the z-axis coming out. So in this case, we'll be using the z-axis. So to calibrate the accelerometer, you want 2 data points and then find a linear curve in between. So holding the accelerometer flat, put it on a flat surface, that gives you an acceleration of 1 gravity, so 1 g, which is either 9.8 meters per second squared or 32.2 feet per second squared. And then you'll put the accelerometer in position where z is coming out horizontally. So that will give you an acceleration of 0. So using those 2 data points, you'll solve for your line, and then with your line, you'll put that in your formula on LabVIEW, and you're good to go for the entire lab.